Hello, Mr. Aaron, Mr. Ryan. Are you alright today? Good. Okay. So today we talked about another problem in the metric. Okay, in the metric. So look at this metric. Okay, I have these. Yeah. So this is the 4 times 5, 5 times 4 metric. So can you find the largest area? What's the area? Largest area of a square metric. Square. You know, it has to be square. Yeah, square.
Yeah, that's what I was gonna say.
Yeah. So that's 9, right?
But it could also
9.
be 16.
No? Why is it 16? Why is it 16? No. You can't find any 16. Right? The ones means you can't include the 0, yeah? 1. We want to find the largest square. Largest square submetric. Okay? Submetric. Yeah? With 1, yeah? With 1. Okay? The problem is clear, yeah? How can we do this? How can we do this? Eric, Ryan, any thoughts? Any thoughts we can do this?
Brute forcing.
Well done. How can we brute force?
By using the brute force.
How can we brute force?
By brute forcing.
What's brute forcing mean? Try every...
Possibility.
So what are we trying here?
Checking
what?
Square.
So we want to check every square, right?
One.
Okay, so that's easy. We want to try... Yeah, brute force will work, okay? Brute force. Well done, brute force. So we try... How can we brute force? We brute force each... Okay? When we have 1, yeah, we try to brute force the metric. Yeah, if this is 1, right? And look at me, come on. If this is 1, we try to brute force the metric, the square metric, starting the top left corner equals 1, right? And we start to expand it. Yeah, if these all 1s, we update the answer. Yeah, we want to have a count to update the answer. All right. So what's the code would be like? So for R in range rows, for C in range columns, right? And if metric RC equal 1, then we can start a size. Yeah, we can say for size S equal S range from 1 to what? To the minimum. To the minimum of the when it reaches border, right? And then we need to check this metric with the size S. So we start with the coordinate RC, and with size increasing, right? Size from what? 1 to something, yeah, to something. We can put it infinity, but actually it's not infinity.
I just said something.
Yeah.
I didn't know it.
Eric, do you understand me? And then we check if the metric if this square metric it contains all 1s. If it's all 1s, then we update the answer. So what's the time complexity? If I don't write the code, if I just tell you this is brute forcing, what's the time complexity? This is, look, we iterate with ORC, right? R times C. But we need to check these.
The matrix.
Yeah, check the matrix. So what?
I don't know what's the matrix.
So look, if this metric here, you check it.
I don't know what did you call the matrix.
Sorry, what did you
You didn't call the matrix a name.
What's the matrix name? It doesn't matter. Look, if this is size R, another R, it could be R.
What's the matrix name? The matrix.
Matrix name. M, for example, M.
Then it's a M.
No, M matrix, it has R, column, C.
M.
So look, look, for example, just give one example. Look, if you start from the top left corner, right? And that's a 1. And then for each, you want to check if all the R rows and C columns are all 1. So it needs to take another ORC time, right? Right? Checking will take ORC. Right? And then each one could be 1. If we consider a metric containing all 1, right? Right? This is a very special case. We need to go through each pixel, right? Because each pixel is 1. Alright? And then for each pixel, I want to check if the largest, what is the largest submetric, right? So I need to expand this, right? Look, for here, I need to expand this. So let's another RC. So together is OR squared C squared. Got it? It's very slow, right? If R and C is big. Make sense? Make sense?
Yeah. Yeah.
Makes sense, yeah? Makes sense. So we can do this, the thing is that why this is slow? Because every time you're checking, you have this duplicate checking, right? Because look, if I check this, this is the metric. It's all ones. And then when I check this metric, I already know this is a metric, right? So I have to check it again. So it duplicate. You get it?
Yeah.
So for example, I'm here at this point. I'm at this point. Okay, Eric is here. Yeah. Eric's here. Okay, I want to check this small metric. Okay, all ones. Good. I know it's a square metric of 4. But now I want to check here. So I still need to check here the small one, right? Right. And I want to check all the ones. So it's duplicate efforts to checking the sum metric. Okay. So we can save it. So we don't want to repeatedly do that again and again because that's slow. So in some way, we want to use the dynamic programming to save the intermediate result. Okay, so how can we do this? We can create a metric of DP array, right? With the same size. If R column, R rows, C column, we want to create a metric with R rows, C columns, which is the same size, right? And then what does it mean? It means that from this means that the array, the submetric, the area from 0, 0 from the top left corner to RC, yeah, DPRC. In this area, the largest square submetric. Does it make sense, Eric? So this number here represents the largest square submetric. Yeah. If we define it as the side, right? The side is, and how can we get the area? So if a square has the side n, what's its area? It's an easy question. If a side equal right? Eric? Ryan? If a subsquare which is side of 4, what's its area?
16.
Yeah, okay, if a square is n, what's the area?
N square.
Well done, good job, yeah, n square, okay? So let's store it as n, the side, the largest side, right? So now look, if I'm here, okay, I want to process this point. So I already know the largest square here, right? And if this is 1, this is 1, this is 1, this is 1, then the answer would be the minimum of these 3 points plus 1, right? So look, I want to update this DP R plus 1, and C plus 1, right? If this is 1, right, Eric? If this is 1 and this is 1, and this is 1, so what can I get? The answer of DP R plus 1, C plus 1 is the minimum. It's the minimum of all these, and then plus 1, right? Yeah, because I can just extend it by 1, right? I can extend it by 1 because it's all 1, right? Got it? Yeah, this is the DP array, yeah? And DP 0, 0. If it is 0, what happened? If this current point is 0, then DPRC is 0, right? Because there is no point. Am I right?
Yeah.
Does that make sense?
Yeah.
Yeah?
Yeah.
So can we write it? Can we write it?
Yeah.
Okay, let's write it. Okay. Define largest subsquare metric. Okay, M, and then let's say RC equals length M, and column will be length M what? M what? M what? Come on. What's the columns of M? And length of M what? Put a number here. Put a number.
0.
Yeah, well done. Oh, now I want to create a DP array. Yeah? DP array equals at the beginning 0 for underscore in range columns, right? The columns. And then for in range M.
No, it isn't.
Range M. So this creates what does this do? What's this do? DP array. This creates what? A 2-dimensional array which contains all 0, and then you'll be the same size of n, right? So you'll be R rows, and C columns, R rows, and C columns. Okay, and all 0, yeah, all 0. Okay, so now I just need to go through each one. Yeah? For R in range R, for C in range C, right? Right? Okay, I go through each one. And if metric RC equal 0, right? If current point is 0, what does it mean? Yeah? It means that, it means what? There's no metric ending. Okay, so the DP array, I may make a mistake. DPRC means what? 0 to 0. So it means that when it ends, so the largest square metric ending at RC here, right? Ending at RC, okay, at this area. So if MRC equals 0, then we need to set DPRC equals what? If this is 0, can it form a square metric ending this one?
No.
No, so we set it to
0.
well done. Else is 1, right? Now we also we have an answer. Answer equals 0. We want to return the answer, which is the answer will be return answer times answer. Okay, answer times 2. Answer square, because answer is the largest side, not area, and the area is square, right? Okay, then what should we do? If R bigger than 0 and C bigger than 0, okay, right? And what? And then you can say MR minus 1C equals 1, right? And yeah, look, I'm at this point, RC. I'm at this point, 1, okay, here. This is RC. And then I have a few here, metric here. I'm at this point, right? So if it's bigger than 0, if it's on the boundary here or here, you can't form bigger metric, right? Because it's on the boundary. But at other places, I want to check this one. It's for this one. This is 1. This is 1. And then I want to, if these 3 are all 1s, yeah? And R C minus 1 equal 1. And can you, what's this point? And what? What? And what? Eric, what's this?
1, 1.
R minus 1 and C minus 1, right? Look, this is RC and 1, yeah? And then what do we do? DP RC equals the mean of which 3 numbers? Which 3 numbers? It will be DP mean of DP R plus minus 1C and DP R C minus 1 and DP what? Can you tell me the third one? Come on. DP R minus 1, R minus 1C, R C minus 1. And what's this one?
R minus 1, C minus 1.
Yeah. I want to get the minimum of this, ending this, and then what? Do what? Plus 1, right? Plus 1. Yeah. Got it? Plus 1.
Yeah.
And once I plus 1, I at this point here, I can do this. Answer equals maximum answer DP RC, right? So I then can get the largest side of this of the answer, right? And then return this. Yeah, got it? So this is the DP function. Plus 1. So why is it faster? Because we already know, yeah? We already know when we want to calculate this, right? We already know what happened in the previous one. Yeah? We already know what happened previous one. Right? Previous one. So square metric, I just added 1 and that'll be it. Right? Yeah? Got it? Yeah? Okay, so now what's the time complexity if you look at this code? How many loops? How many loops are there?
They are 2.
2. So R
And square.
R times 3, yeah? R times 3. What's the space complexity? Are there any space? Are we using a space DP array? Yeah. So what's the space complexity?
RC.
Oh, RC. Right. Okay, can you explain to me why we put answer? Answer equals max answer, DPRC. What does this do?
Because we need to find the biggest square.
Biggest square ending, yeah? What could be the biggest square? It could be, the biggest square could be ending at RC each location, yeah? Ending at large location, right? Okay? Yeah? Okay. And then we return, why this is answer comes to, what does this mean?
It means that we
What's the answer and what's answer times soon?
answer
Is what?
is when we know the
largest side of a square, right? And then we need to times to, what does it mean?
because you have one side of square and you deal with the other side.
Yeah, it's the formula to compute the area given the side, right? Like if a square, the side has 5, then its area is 5 times 5. Yeah, that's what exactly that does it. Okay, and what's this part? If MRC, if this is a 0, what does it mean? If this is a 0, why we need to set DPRC equals 0?
Because if it's just 0, it wouldn't be, yeah.
The side of ending at RC, there's no, right? Because you can't find, look, this is 0. I want to ask, there's no way to find a metric which ends here, right? Because this is 0, right? There is no way to construct a metric, square metric, ending at this point, which is 0, right? Right? Got it? That's why we set it to 0. Got it? Does it make sense? Okay, DPRC is a dynamic programming array, yeah? 0 for range and C columns, and then subset of magic, yeah? Okay, that'll be it. Okay, thank you. Good job today. Bye bye. Say bye bye.